This is an introduction to flipped learning for A2 students. This is how we'll be doing lessons this year. I'm going to use gravitational fields as a topic. We'll cover the key concepts and do a couple of calculations at the end. So let's get started with gravitational fields. Gravitational fields are created in the space around objects with mass. So mass is the key physical quantity here. And other objects with mass experience a force when they're in a gravitational field. So G is the symbol for gravitational field strength. So the gravitational field strength at a point is the force exerted per unit mass at that point. So that's G, and from that definition, that's the definition, we can get this equation, F divided by M, so force per unit mass there. And the units are newtons per kilogram for G. So that's the equation that's linked to the definition. Gravitational fields, they have a direction, and it's always towards the centre of the mass that created them. So created the field. So if this is my mass here, which has created a gravitational field in the space around it, then the field direction is always towards the centre of the mass. And these blue lines here, those would be gravitational field lines. They're entering the surface of the mass at right angles to the surface there. So that's our G. As you move away from the mass, the gravitational field strength will reduce. So it gets smaller as you move away from it. And the reference point is always the centre of the mass. So from the centre of the mass, as you move away, we call that distance r, G decreases. It decreases according to an inverse square law. So G is proportional to 1 over r squared. You've seen an inverse square law before when we looked at wave intensity. The full equation then is G equals minus Gm over r squared. It's important to note that this is not the equation that defines gravitational field strength. This is the equation that is linked to the definition. But this is another equation then that we can use. Some things to note about the equation. Firstly, we have a negative. That's there because the field has a direction which is towards the centre of the mass. So that's what that indicates. G is the universal gravitational constant. So it's a constant value. The value of that is 6.67 times 10 to the minus 11 newtons. 10 to the minus 11 newton meters squared per kilogram squared. That's given in data books, so you won't need to memorise that value. If you need it, it's in the book. M is the mass of the object that's creating the gravitational field around it. And r, as I said, is the distance from the centre. Right, so that's that equation. Now, what if you have two objects with mass? As I said earlier, if I have one object, it will create a gravitational field around it. Another object with mass, so one object with mass, another object with mass placed in that field will experience a force. So there's a force between these two objects, and vice versa, of course. The other object that I put in, so if I put a red object here, that's my smaller mass there, that has a gravitational field around it, so that's going to exert force on M. The equation, or the law rather, actually I'll write it on the left over there. Newton's law of gravitation. That says that the force between two objects with mass is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So if I had M and, well, let's call it M1 and M2, then there's a distance here, that's R, So the force is proportional to m1, m2, and force is inversely proportional to r squared. The proportionality constant is the same as the proportionality constant here. It's g, and this force is always attractive, so there's a negative here. So it indicates direction. And that would be the full equation there. So the blue pen to highlight my equation. So that would tell us the force between two objects with mass. And note that the R is from the centres of mass, so it's the centres of mass there. The force that M1 experiences due to M2 is equal, but in the opposite direction to the force due to M1 on M2, and you could confirm that with that, where you can see that the only thing that's going to change is the position of the masses. The R is the same, so you always get the same force, just in opposite directions. Last thing to cover is the graph. Hopefully this will fit in here. Yeah. So we have the graph of gravitational field strength with R. If this is for our object here, let's say it's got mass m and it has a radius of r. When we're dealing with things like planets, then we'll just talk about an average radius there. But yeah, this is for objects of mass. So, and at r, this would have a value of g0, I'm going to say. So g0 occurs at the radius r. And now we can mark up 2r and 3r here. And this is an inverse square law, so graph will look like that, and at 2r the value would be g0 over 4, and at 3r it would be g0 divided by 9. So that's what the graph would look like, and some of the key points there, and then you could work out additional points as well to plot on that graph. So that's the graph, and now we'll move over to do some calculations. I'll clear the board so that we can do that. Okay, let's do some calculations for gravitational fields. Up here, I've got the equations that you'll need to be using, and down the left here are some data values that you'll need to use as well. So we've got the mass of the Earth, 6.0 times 10 to the 24 kgs. The radius of the Earth would go here. We're actually going to be calculating it in the first one, so I haven't put it in here yet. The mass of the Sun, 2.0 times 10 to the 30 kgs. The radius of the Sun, 7.0 times 10 to the 8 meters. The distance between the centres of the Sun and the Earth is there, 1.5 times 10 to the 11 meters. And then the universal gravitational constant, value you've already seen, 6.67 times 10 to the minus 11 Newton meter squared per kg squared. So using that data, these equations, we're going to do a couple of calculations. Question 1 is to calculate the average radius of the Earth. In addition to this data, you'll need to know one other value, but it's a value you should know, so I'm not going to give it to you right now. I want you to have a go at solving that, so pause the video and have a go at solving it. And if you need a hint, then the value that you need to know was that G at the Earth's surface is 9.81 newtons per kilogram. Hopefully that helps. So then you can have a go at solving that problem. Okay, question 2. Calculate the distance above the Earth's surface where the net gravitational field strength between the Earth and the Sun is 0. So we now have an additional piece of data, which is the radius of the Earth. So we've got this data, these equations. Have a go at solving this problem. Calculate the distance above the Earth's surface where the net gravitational field strength between the Earth and the Sun is 0. So pause the video and have a go at solving that. If you need a hint here, then what you're trying to find is the point where the gravitational field strength of the Earth is equal to the gravitational field strength of the Sun. sure you appreciate if the sun's over here and Earth is over here, the gravitational field strengths have opposite directions. So if the magnitudes are equal, then they will cancel out, giving us net zero. So that's what you're trying to find. So now, if that helps, pause the video and try solving it now.